Today we are taking a first look at Ennova CFD. Here we will be using Ennova CFD to perform a complete CFD analysis of flow in a pipe. For this tutorial we will be using OpenFOAM as the CFD solver, but the choice of CFD solver is yours, which is a key benefit of Ennova CFD. So let's get started. First we need to import our geometry. In this case we have a file called pipe. Once we have opened the file, one thing you will notice about Ennova CFD is that many of the commands can be obtained by the right mouse button, which is context sensitive and displays common commands relevant to the current situation. To help clarify the tutorial, you will see the mouse clicks in the lower right-hand side of the video. In this case we have chosen to hide the surfaces and display the surface edges, which as you can see are currently colored red. Let's look at these red edges and select one of them. Using the menu via the right mouse button, we can select the command Select Attached Edges. Here we see only one face is connected to the red edge. We refer to red edges as single edges. What we want, of course, is every edge to be connected to two faces. We need to stitch the model together so all the faces are connected. Making this so in Ennova is called repairing the model, and we use the function with the band-aid on the top menu. Many types of repair is possible with this command. Merging surfaces, removing slither surfaces, and clearing intersections are some examples. The repair function typically handles the work automatically, but like most functions in Ennova, it can be manually directed if necessary. The repair is controlled by the settings menu, and here we see the merge tolerance is initially set to 0.02 mm, which we will accept. Pressing the band-aid repairs the model, which results in black edges and the associated enclosed volume we need for the CFD analysis. Black edges signify the edge is connected to both surface neighbors. The next step in the process is that we want to organize the geometry into groups with names that will help us with boundary conditions later on. Using our usual right mouse button technique while hovering over the geometry allows us to turn all the faces on. Now we can zoom in and start moving surface faces to appropriate groups. Select each region in turn by selecting the surfaces required for the boundary condition. If more than one surface is required, hold down the Ctrl or Shift key while selecting the additional surfaces. Again, use the right mouse button to move the selection to the desired group. Repeat this process for each boundary condition needed: inlets, outlets, symmetry plane, etc. So far we have been selecting from the 3D geometry. Selection can also be performed directly from the tree. Here we select the remaining groups of the model that make up the wall boundary condition by directly selecting from the tree. Notice the Shift key to collect all the groups in the range. The geometry is now complete and watertight. Ennova constructs the CFD mesh by meshing all the surfaces first and then filling in the volume mesh. The volume mesh is performed in 3 steps. First, the viscous prism layers are extruded from the surface mesh. Next, a tetra-volume mesh is generated. Finally, the entire mesh is converted to the polyhedral or honeycomb mesh we require for OpenFOAM. This can be done in a sequence of steps in Ennova or automatically in one command. To set up the meshing in Ennova, use the top ribbon and select the Mesh tab. There you will see the Mesh Setup panel. Use the Mesh Setup panel to access the global mesh parameters. Here we set the size of the mesh. We are using a maximum cell size of 0.1 and a minimum of 0.005. The refinement number controls curvature and is best explained if your geometry was a circle. This is how many points there would be around the circumference. The sag number can also be used and is the inverse of this number. This case we choose 12. This way Ennova will automatically refine the mesh to resolve any changes in curvature in your model. Other settings for the mesh control are available in this panel as well. For example, we can allow the surface mesh to have both quad and triangle elements, which we will choose for now, or restrict the model to only triangles. We are now ready to mesh the model. To explore our meshing parameter space, we can restrict initially Ennova to only mesh the surface mesh. This way we can experiment with different settings to obtain the ideal mesh. Let's proceed and mesh the model to these settings by pressing the topology mesher icon. Rectangular regions can be automatically mapped to a quad surface mesh. An all triangle mesh can be generated by selecting the all triangles option. As there is already an existing mesh, we have the option to overwrite it or save the existing one when we mesh again. This results in an all triangle mesh. For a simple mesh, visually checking the mesh is appropriate. For a larger mesh, this is impossible, and Ennova provides a series of tools to check the mesh. It is important to note different CFD solvers often require different mesh metrics depending on the solver and the physics. The check mesh icon is the stethoscope. We see the mesh, not surprisingly, is good. Opening the control shows the various tests it can perform. Further tests are easily performed and available from the Check tab. In this case, we have selected the mesh quality. Results can be viewed in graphical form to identify regions of concern. To proceed with the volume mesh, we first define the global parameters for the prism layers. The control sets the overall maximum parameters for the layers. Ennova may use less layers if the mesh becomes isotropic or intersections occur. In this case, we choose to have 8 layers, with a first layer height of 0.001 and a growth rate of 1.2. The first layer height may be varied over the model to control the Y+ value as needed in your analysis. Other more detailed controls for the prism layers are available for advanced users. Not every surface in the model requires viscous boundary layers. We only need to grow the prisms from the physical walls. Selecting the local parameter icon gives us the control to select the wall group. We then turn the prisms on for this group. After making your selections in this panel, use the Apply Meshing Parameters to save your choices. Each group can individually have its parameters set, or if left blank, the global parameter settings will be automatically applied. For advanced users, a spreadsheet view of the local parameter view is also provided. That completes the parameter setup for the mesh. The remaining steps are to instruct Ennova to compute the correct volume mesh. We do this by using the Tetra Mesh control, an icon with the yellow triangle, and turn on both polyhedral and boundary layer mesh checkboxes. The last step before we mesh is to remember we had previously set the mesher only to compute the surface mesh. So now we need to change it so it computes the volume and prism mesh. With all that done, it just remains to run the topology mesher using the topology mesh icon in the usual way. Ennova will now proceed and mesh our complete model. We see Ennova now has computed a volume mesh. Let's take a couple of minutes to explore it. Looking around the mesh, we see the prism layers have slid along the inlets and symmetry plane as expected. We see the prism layers and the honeycomb type mesh. So it all looks good. Let's use the check mesh to verify that everything is okay. Before we used this tool to check the surface mesh. The same tool will also work on the 3D mesh as well, so Ennova correctly reports all is well with the mesh. Next, we choose the orthogonality check. We know this is very important quantity for OpenFOAM. Here we see the mesh is all within valid ranges of orthogonality with no elements out of range. This now concludes the mesh generation part of the tutorial. We will be continuing this tutorial by demonstrating using OpenFOAM directly integrated inside Ennova. However, in general, the mesh can be exported to a number of other CFD solvers so they can be run externally. Before moving on to the OpenFOAM section, let's look at a couple of other areas of Ennova functionality. First, at any point you may wish to save your Ennova work. To do this is simple. The Ennova project is saved by saving the case file. The extension is .ecf. All information is stored in this single file. So far we have just looked at the Ennova mesh on the surface. By choosing the Slice command from the Check tab, we can define a plane to slice through the mesh. This plane is by default axis aligned, but the Rotate and Shift handles lets you freely position it. Once adjusted to the desired location, the Extract button is used to create the slice. which we can now see the resulting slice through the mesh. To best view the slice, close the slice tool, and from the group tree you may turn off the mesh. The slice can then be viewed as its own object. OpenFOAM is a Linux application. Fortunately, recently Windows allows Linux to run a Linux shell native on the same machine Windows is installed on. From Windows 11, make sure WSL2 is installed on your computer. If WSL2 is not installed on your Windows computer, this can be done from the Turn Windows Features On and Off menu. Simply enable the virtual platform and Windows subsystem for Linux and then restart your computer. Once this is done, visit the Microsoft Store and download and install Ubuntu. That's all there is to it. With WSL2 installed, we will be able to run OpenFOAM directly from the Ennova UI. OpenFOAM using WSL2 behaves to the user as just another program running on your computer. It just happens to be running in its own virtual Linux computer, which shares the same directories and files as your Windows computer. Using OpenFOAM from within Ennova basically means that all your interactions are from Windows. No Linux experience is needed. So let's see how it works. First, open up the Setup OpenFOAM tab. Basically, to perform an analysis in OpenFOAM, we will move through these tabs from left to right. Each tab is organized by its function. For this tutorial, we will accept many of the program defaults for clarity, but these all may be set individually depending on your analysis required. First, the DT icon. To start off, choose the version of OpenFOAM that is installed on your computer. In my case, it is V2012. Next, we can use the default settings for an incompressible CFD solution using the SimpleFOAM solver. We can use the Scotch method of domain decomposition for allocating which parts of the mesh are processed per CPU core. We can now proceed to the next icon, which controls the way the equations are discretized and solved. We will accept the defaults. We have chosen so far a parallel, steady-state incompressible turbulent solution using RANS. We also now must instruct OpenFOAM about what fluid is inside our pipe. Here we will choose air as the working fluid. We now need to link our computational fluid that we have chosen, air, to our mesh volume. We can also set here the initial conditions of the volume for the coming analysis. We will need to set initial conditions for all the variables we are solving for in the domain: velocity, pressure, and the two parameters for our turbulence model. Each Ennova surface group now needs to be assigned to an OpenFOAM boundary condition type. We will start with Inlet 1. This is the larger of the two inlets. The inlet boundary condition is easy to set up, although care must be taken to make the inlet velocity vector point into the domain and be normal to the inlet surface. Inlet 1 is set to boundary condition type inlet. We are then able to apply the correct inlet velocity of 0.5 meters per second in the positive x direction. Moving along to the second inlet, which is the smaller one, we have a velocity of plus 1.2 meters per second in wide, as this inlet is normal to the y-axis. The inlets also prescribe the turbulence intensity of the inlet flow, which we are leaving to the default values of an intensity of 0.03 and an eddy length scale of 0.03. We then proceed to assign the outlet, symmetry boundary conditions, and lastly the non-slip walls. After this is completed, our model is ready to run. Now we have our model completely set up. All that remains is to save the project to disk where we want OpenFOAM to run. Before we do this, we need to instruct Ennova we wish to run OpenFOAM on WSL. Once this is done, exporting the OpenFOAM project will save all the files OpenFOAM needs to run. In our case here, I have chosen to run in a folder pipe. Pressing Run launches OpenFOAM. This model is very small and runs in just a few seconds. The Linux shell closes automatically when OpenFOAM finishes. We now have a completed CFD solution. We can now use Ennova to post-process or visualize the results. We will only scratch the surface in Ennova's capability here, as Ennova sports a fully fledged post-processor. By choosing post-processor, we can navigate to our pipe directory. To open an OpenFOAM analysis, load the file post.foam. A convenient place to start is to color the boundary conditions to represent pressure. That concludes the demonstration for today. Ennova CFD can be downloaded for a free trial from www.ennova-cfd.com.